one of my research group, the randomized quasi-Monte Carlo and the Owen's boundary growth condition with spectral analysis. So today we'll discuss we'll study the variance of the randomized quasi-Monte Carlo estimator with two of the contemporarily most commonly studied low discrepancy sequences, the rank 1 lattice rule and the Sobol sequence. We'll use the Fourier and the Walsh-Fourier analysis for the spectral analysis. Well, the Walsh-Fourier basis is equivalent to the higher wavelet basis. And the subject that we'll study are the unbounded integrands satisfies the Owen's boundary growth condition. We'll not discuss how to design the good QMC quadrature. We suppose that we already have good ones from these earlier literatures. We'll only talk about the finite dimensions, and we'll only talk about the asymptotic convergence rate of QMC. The problem that we want to study are the following integration problem. That we consider the integration in this s-dimensional unit hypercube of the integrand f. But more often, this problem comes from the integration in the RS. So in that case, if we want to apply the quasi-Monte Carlo, we need to apply the inverse transformation. We need to apply the transformation from this RS to a unit hypercube. And this is usually done by the inverse CDF of this given distribution. And this kind of randomized approach for the integration has applications in the literature. For instance, you want to compute the quantity of interest from a random PDE models, or there are finance applications like computing the price of options. So here I'm given the 64 points of Monte Carlo and these two types of quasi-Monte Carlo quadrature in space. And these low discrepancy sequences try to distribute the points more evenly into this unit hypercube. The Monte Carlo estimator is just the average of the function evaluations at the IID samples in this unit hypercube. While quasi-Monte Carlo estimator replaces these random samples by the given deterministic points. The result is biased, so that we need to introduce the randomization in order to get to the unbiased randomized QMC estimator, where this circle plus denotes the randomization operation. And in the case of lattice rule, we can apply the so-called random shift that we have this delta R, which is a random variable in 0, 1. That we apply this to the set of lattice points to get this randomized QMC estimator. This is unbiased, and also it provides the variance estimate for the variance of this RQMC estimator. The variance of such a RQMC estimator is the one that we want to study today. The error of the QMC is given by this classical Cox-Mahoraka inequality that the error can be bounded by the product of the Hardy-Cross variation of the integrand and the star discrepancy of this low discrepancy point set. And for functions that are smooth enough, you can compute this Hardy-Cross variation. And for the function whose Hardy-Cross variation is bounded, that the QMC error is given by this n to the -1 times log term. If we just look at this formula, then we have an issue when the dimension is large, because this n to the -1 times log n to the s only decreases when n is large enough. But the observed empirical convergence rate can reach n to the minus 1, even with a realistic large n. And the reason is that you have a small, sometimes you have a small effective dimension. But this is not the topic that we'll discuss today. We'll discuss today that there are some L2 functions whose Hardy-Cross variation is infinite. In that case, the Cox-Maholoka inequality fails to be informative. And here we'll give 3 examples of integrands who has an infinite Hardy-Cross variation. The first example is that when the integrand has the boundary unboundedness, so Owen characterized this kind of integrand using the boundary growth condition. So more specifically, that the mixed first order derivative is bounded by the product of this J from 1 to S dimensions, and in each dimension, the distance to the boundary, so it's Tj or 1 minus Tj to the power minus 1 minus Aj. And because we consider L2 functions, so this A has to be less than 1/2. And Owen proves that for a function satisfy this boundary growth condition, the L1 convergence rate for the general low discrepancy sequence can be n to the minus 1 plus epsilon plus the maximum of these AJs. And one example is that you want to compute the expectation of f, and f is given by the exponential of the summation of this inverse Gaussian CDFs, where this t is from 0 to 1. So this is equivalent to compute the expectation of log normal random variables. In this case, if you compute the derivative, you can have this A equals 0. So in this case, you would have order of n to the minus 1 plus epsilon, which is the optimal rate if you if you compare with the Cox-Maholoka inequality, but the approach is different. The second example involves the interior discontinuity. That if your integrand is f is given by the product of the indicator function. So indicator function is that if t is inside this omega, then this is 1, otherwise this is 0. And omega is a subset of the unit hypercube. And g is a bounded function. In this case, the authors, He and Wang, they proved that for the Sobol sequence, the L2 convergence rate is given by n to the minus 1/2 minus some term plus epsilon. And this term depends on the number of axes that are not parallel to the discontinuity boundaries. So the more, the less parallel to the discontinuity boundaries, the larger this denominator, and then the closer you get to the rate of Monte Carlo. So one example that takes the form of this indicator function, if you have this discontinuity boundary given by the T1 plus T2, that is equals 1, then you have 2 axes. So essentially the first and second one that are not parallel to this discontinuity interface. Then you would replace this du by 2 in this formula, and in the end you result in n to the minus 2/3 plus epsilon. The third example is a combination of the previous 2 examples, that you both have the discontinuity, interior discontinuity, and the boundary unboundedness. The example considered by He in his paper is still given by the product of this indicator function and the g, but now g is unbounded and satisfy the boundary growth condition. So the author proved that for the Sobol sequence, the L2 convergence rate is given by order of n to the this power, and this power is a product of essentially the first part is related to the boundary unboundedness, and second part is related to the interior discontinuity. So as if the effect is a multiplication of these two factors. And later in this talk that we'll see that actually this rate can be further improved. One example of such integrand is given by this European basket option that you want to compute the expectation of an integrand of the stock price at final time t, that you compute the expectation of the summation of these stocks minus the struck price k, only if when this value is positive, and follow the standard assumptions that of these SDEs of these stocks. In the end, you can have the explicit formula for this S, and you compute the expectation of this form. So here, this is the summation of some constant times the exponential of some constant plus the inverse CDF, the inverse CDF of some uniform random variables. And this has the singularity when this UJs equals 1. This is the unboundedness, and also you have the discontinuity because you only consider when this value is positive. So now we want to introduce the spectral analysis for these two types of low discriminant sequence. First, we want to study the rank 1 lattice rule. And we're familiar that the formulation of this lattice rule is that first you have a generating vector, and the lattice rule with n quadratic points is given by z over n times I modulo 1, with I iterating from 0 to n minus 1. And the randomly shifted lattice rule is just apply a random shift to all of these points. And we want to study the variance of such RSLR, random shifted lattice rule estimator. We want to use the Fourier transform to study the lattice rule. At first, we consider that the function is periodic, and then we can apply the Fourier transform, and we use f hat to denote this Fourier transform. You can also equivalently write it using this Fourier coefficients, where the Cn is given by the integration in this unit hypercube of f with this term. And we also introduce this ensemble operator that we have n points and lattice points, and this Sn is given by the average of these Dirac delta functions at these centered at these points Ti's. With these notations at hand, we can rewrite the integration estimator as the inner product of this ensemble operator and the integrand f. Because these are Dirac deltas, and then you apply this inner product, you get this lattice rule estimator. And then you apply the Fourier transform of this L2 inner product. You get the inner product in the frequency space. And then you constrain these frequencies at only these integer frequencies. So this is what you get. And this S hat is just the Fourier transform of this sample operators. And now we want to express the variance of this term. So we compute the second order moment, and we subtract the first order moment squared. The result from the result is already in the early literature. that the variance of such random shift estimator is given by the summation of all these integer frequencies except 0 of the norm squared, the Fourier transform of this sample operator, and the Fourier coefficients norm squared. Actually, the equation 16 holds for any general deterministic points. So that means so far we haven't used the property of the lattice points. If we use this shorthand notation, the power spectrum density as the norm squared of this Fourier transform of the sample operator, this power spectrum density of the lattice is either 1 or 0. It is 1 if the frequency times the generating vector modular n, modular the number of samples, is equivalent to 0. Otherwise, this is 0. So that means you only sum the norm squared Fourier coefficients at these ones. This is also known as the dual lattice. You only sum this when n times z modular n is equivalent to 0, except the origin. So the variance of the variance of the lattice rule estimator is given by the squared Fourier coefficients of the integrand at the dual lattice except the origin. In these two figures, I'm giving the example of the lattice rule with this generating vector. This is also a class of Fibonacci lattice in dimension 2. That I have this generating vector, and the number is 21. And in this right plot, I'm plotting this corresponding dual lattice. If we compare with the Monte Carlo, the variance of the Monte Carlo estimator is given by 1 over n times the summation of the norm squared Fourier coefficients, except at the origin. If we consider this example, this 1D example, this is unbounded integrand. It blows up at the boundary. This function has the decay of the Fourier coefficients with the decay rate. The decay rate is connected with this power here. In the case of Monte Carlo, which is this pink color in the plot, that this norm squared Fourier coefficients decays with 1 over n for all these integer frequencies except the origin. So this is the plotted as this pink color in this plot. And the lattice rule, when you increase n, the lattice rule will discard some of these frequencies. So this orange color is actually an upper bound for this this RSLR estimator variance. So this is how the Monte Carlo and quasi-Monte Carlo behaves differently in this spectral domain. So now we want to characterize the decay of these Fourier coefficients. That Niederheit introduces this function class epsilon alpha. Given a constant, this Fourier coefficient is bounded by the product of R1 of nj to the minus alpha. N is this nj is the frequency in the jth dimension, and R1 is the maximum of 1 and the absolute value of nj. This is to avoid that some of these frequencies becomes 0. So you have this decay. He introduced this kind of function because Niederheit uses this decay to derive the L1 convergence of the lattice rule. But in this work, we want to study the variance, so we can extend the range from alpha larger than 1 to alpha larger than 1/2, because then we square this Cn, and we still satisfy the summability condition. If you have the decay of such Fourier coefficients, then there's an existing result. There exists a generating vector such that you can achieve this kind of the variance of this randomly shifted lattice rule can achieve this convergence result. So now we want to answer the question that what kind of function has this kind of Fourier series decay? In the literature, Zaremba characterized a sufficient condition for the function f belong to this space. He considered that when alpha is an integer, and all of these partial derivatives with these powers k that is less or equal than alpha minus 1. So suppose this alpha equals to 2, then you have this mixed first order derivatives. If these exist and are of bounded variation in the sense of Hardy-Grant cross, then you can have this f inside this class. And we want to characterize the decay of these Fourier coefficients and Owen's boundary growth condition. So what we can prove is that first we consider the one-dimensional function f, and this is the f is not necessarily bounded. We have the derivative that satisfies the boundary growth condition. With alpha that is larger or equal than 0, less than 1/2, we can prove that the Fourier coefficient satisfies this. I think I'm missing an absolute value here. Yes, so the absolute value of this Fourier coefficients satisfies this decay. So when a is positive, you have n to the minus 1 plus a. And when a equals 0, you have n to the minus 1 times some log factor. So you can use this result to also to prove the variance of the convergence of the variance of the lattice rule estimator. But now the problem is that we want to further investigate when a is negative. That is to say that when a is negative, the function is no longer unbounded. The function f is bounded at 0 and 1. That means in this situation, can we further exploit the regularity? The answer is that we cannot further exploit the regularity if we don't impose further regularities. So in this case, if we only have this condition, the result that we can get is that the Cn will decay as order of n to the minus 1. So it's independent of A. So next we want to impose a further regularity on the derivatives of this integrand. So now we have this A bar that is less than 1. And we consider the k to be an integer, including 0. We still consider the 1D function. And we have three assumptions. That the k minus 1 derivative is continuous on the torus. The k derivative, we are only assuming that this is piecewise continuous, that it can have a finite number of discontinuities. And the k plus 1 derivative or the derivative satisfy the boundary growth condition. for some a bar that is smaller than 1, which is given by this. And when this k equals 0, we denote this -1 order as the integration. So by this, we also include the case that we discussed in the last page. If we have these assumptions, what we can get is that still I'm missing the absolute value here. The absolute value of Cn is given by these 3 cases. If this A is positive, then we have n to the -1 minus k, that is depending on the high order derivative, the kth order derivative, plus a bar. And if this a bar equals 0, then we have n to the -1 minus k times log term. And if a is negative, in general, we cannot get anything that is better than n to the -1 minus k. If we compare this assumption with the Randomized condition, first we want to compare this with the necessary condition, that if this Cn has this decay n to the -1 minus k minus epsilon, then it is necessary that f is in ck of the torus T. So in our context, these 2 conditions are our additional assumptions: the piecewise continuity of the kth order derivative and the boundary growth condition on the k+1 derivative. And compare with the Randomized condition, he considers this only the integers, so we let a bar to be 0. And we assume that the kth order derivative is piecewise continuous. And from the boundary growth condition, we can have this kth order derivative to be less or equal than this log of minimum t or 1 minus t. So this term is not necessarily has a bounded Hardy-Cross variation. So we're not assuming this part. And our result is that it's only inferior up to a log factor. And in the case of multidimensional, here I'm only assuming the assumption of the first order mixed derivative, because high orders you can derive similarly. It turns out that in multi-dimensions, the integrand can allow an axis parallel discontinuity, that this f is equals to the product of indicator function and the g, with g satisfy the boundary growth condition. And this set is axis parallel. So it's a tensor product of aj and to bj. In this case, we can have the decay of this Cn as the product of R1 of nj to the -1 plus a. So this fills the spectrum of these non-integer convergence rates for functions satisfy certain growth conditions.
Again, Yang, how is
Yes.
the connection between A and AJ?
Okay, this A is should be the maximum of all these AJs. So
Yeah, thank you.
okay, so this concludes the part for the lattice rule, and now I want to talk about the Sobol sequence. First, I want to introduce the notations of the TMS net in base B. Okay, so we introduce this elementary interval, this E of kappa and tau. it's a tensor. It's a form of this tensor product of from j equals to 1 to s. And here you have in the denominator you always have b to the kj, and we have the constraint that the summation of these kj's equals m minus t, and these t's are ranging from 0 to b to the kj minus 1. So you partition this unit hypercube to these elementary intervals, with each elementary interval of volume b to the t minus m. So b to the m is the number of points. That means when you increase m, the volume of each elementary interval is given by b to the t minus m. So it's getting smaller and smaller. And each of the elementary interval contains exactly b to the t points. So this is clear that in some literature, t is also referred as the quality parameter, because the smaller the t, you have the smaller volume of the interval, and it contains less points. S is the dimension, and b to the m is the number of points. The Sobol sequence is a kind of TMS net in base 2. And we let the capital N to be 2 to the m, and this IN Sob to be the scrambled Sobol sequence estimator of this integral. Owen uses the higher wavelet and the ANOVA. So it's a multi-resolution ANOVA decomposition of F. And he derived the variance of this IN Sob to be given by this equation 29. So it's 1 over n. And the first summation is over this u's, and u is the subset of this 1 to s. So it's a subset of the dimensions, coordinates. And L are assuming this n0s. So it's ranging from 0 to plus infinity for all of these s dimensions. The product of the gamma depending on u and l, and the sigma squared u and l. In the book Digital Nets by Dick and Phyllis Sharma, they have an equivalent formulation using the Walsh basis. In Owen's paper, he referred this gamma as the gain coefficient, because he want to compare this one with Monte Carlo. And in the case of Monte Carlo, all of these gammas equals to 1. So you have 1 over n and some constants. And a recent paper that explicitly derived the values of these gammas, the gain coefficients, in base 2. So these gammas are given in this by these 3 situations, that if this L, the absolute value, so summation of the L1 to Ls is less or equal than m minus t minus the cardinality of u, you have this gamma equals 0. So you can imagine that when you increase the quadrature size, that is when you increase the m, there will be more and more these gamma terms that becomes 0. And if this L is larger than m minus t, this gamma always equals 2 to the t, which is a constant. And in between, you have some value in between. So corollary is that the variance of the random scrambled Sobol estimator is never a constant. A constant is given by 2 to the t times the Monte Carlo variance. But in this work, we want to study the decay of this term sigma squared. And for simplicity, we will drop the ANOVA decomposition part. So we will drop this notation U. And we have the variance given by 1 over n times the summation of this L of these terms. And here we want to briefly introduce the Walsh function in 1D. Given an integer k, and this k has the expression in base b. And for a finite k, this series is finite. So after some values kappa, this will be 0. And we denote omega b to be this bth root of unity. And this Walsh function evaluated at x. If you write x also in base b, then this is the omega b, this bth root of unity to the power, and this power is essentially the inner product of this expression, the digits of k in base b and the digits of x in base b. And you can already see that this is already a piecewise constant function. And when you increase k, the resolution increases. This is already equivalent to the wavelets. Okay, so these are some details that you can you can express f using this Walsh basis. And if you define the index set that k is from 2 to the n minus 1 to 2 to the L, and you define the function beta, that is the summation of k, that k is inside this kind of rectangular set of the expansion of the Walsh expansion. And this sigma L squared is given by the variance of this beta L, which is the summation of this Walsh-Fourier coefficient norm squared inside this index set. Okay, so these are like how to compute these coefficients. It's kind of technical. I'll just skip it. So I just show you the results. That for the integrand whose derivatives satisfy this boundary growth condition, you can prove that this Walsh-Fourier series. Sorry, this is not the Walsh-Fourier series, but this is the sigma L's that is defined in the random scrambled estimator. Follows this decay, and this A star is the maximum AJs. With this in hand, you can derive the variance of the Sobol estimator, Sobol sequence estimator, given by n to the 2A star minus 2 times some log factor. And in the proof that I cannot get anything if the A star is not in the range of minus 1/2 and 1/2. So that means currently we cannot prove anything that is better than if the variance is faster than n to the minus 3 times log factor. The previous literature that states some sufficient conditions for this n to the minus 3 variance convergence rate. This literature from 1999 requires that if this f has the generalized Lipschitz condition, and Owen in his proof he requires that the derivative of f is bounded. But in our result, we can get almost n to the -3 variance convergence rate if the derivative satisfy this growth condition for a that is equals -1/2 plus a small delta. That means in our approach, we don't need to have this derivative to be bounded in order to achieve almost as good as n to the -3 variance convergence rate. Not only that, but we also provide the whole spectrum of the convergence rate for the function satisfying different growth conditions. And the observation that the variance convergence rate of Sobol sequence does not exceed n to the -3 is in accordance with the remarks from the book by Dick and Philip. And even if the integrand has a better regularity, so this is in contrast with the lattice rule, because in the lattice rule you can have a higher regularity on the higher order derivatives, and then you can get a faster convergence rate. We also consider that if the integrand also involves the discontinuity, and we consider that this omega to have a partially axis parallel form. So this part of this boundary is general, satisfies some regularity conditions. For instance, it has a Lipschitz boundary, and the rest of them is just that it's a hyper rectangular shaped. And in this case, we can prove that the variance of the random scrambled Sobol sequence is given by these two parts. So this first part is related to this boundary unboundedness, or boundary growth condition, doesn't have to be unbounded. And this second part is related to this discontinuity. So this is an improvement to the early literature. That the effect is not a multiplication, but it's rather whichever is dominating the singularity. Okay. Next, I'll show you some numerical results. That we suppose that we are interested in the integrand given by this the product of this indicator function of and the g. We suppose f is in L2, and g is given by the form of the exponential of m times the L2 norm squared of the inverse standard normal CDF of t. And for this to be L2, we have to impose that m is less than 1/4. And we can verify that the derivatives satisfy this following bound. So we have -1 minus 2m. And in the following, we'll consider various settings of this constant m, the dimension s, and the different types of omegas. We'll use the lattice rule and the Sobol sequence from this earlier literatures. So first, we are considering this hypersphere type discontinuity, that we consider this omega to be the summation of tj squared, that is greater or equal than 1. So it's the hypercube minus this hypersphere. Here we are plotting the lattice rule in this first row and the Sobol sequence in the second row. I'm using different colors to differentiate them. And the columns are different dimensions. The first column is dimension 2, and second is s equals 3, and the third is 5 dimension. I'm computing for each this n, I'm computing 2 to the 11 samples and I'm plotting this box plot ranging from the 1 to 99 percentile of these samples. And this red, this diamond shape is the mean value. And in this page, I'm selecting m equals 0.1, so that 2m will be 0.2. And if we don't have the discontinuity, we would have minus 2 plus 2a. That would be minus 1.6 convergence rate for the QMC. And in dimension 2, we can see that actually the convergence rate is dominated by the discontinuity. That would be minus 1 minus 1 over 2. So we are seeing 1.5 instead of 1.6. And in the second plot, in the second column, we increase the dimension. So the convergence rate is more closer to minus 1 minus 1 over 3. And in the third plot, in the third column, we see that the convergence rate is close to minus 1 minus 1 over 5, which is minus 1.2. And we're still considering the hypersphere type discontinuity, but this time we are increasing m. So for the dimension 2 and 3, we increased m to 0.2. So we see that now the convergence rate is dominated by this m instead of this the dimensions, the number of dimensions. So for this for the dimension 2 and 3, we're seeing that the convergence rate is close to minus 1.2. Well, in the third column, we're seeing, because this m is really close to minus 1/4, which is the boundary case. So here we're seeing more of this non-asymptotic effect. And in the example 2, we consider the hyperplane type of discontinuity, that the discontinuous interface is given by the summation of the TJs that is larger or equal than 1. So in 2D, this interface will be this diagonal line. In this example, actually, this is something curious, and there is something that I cannot answer in this paper, that the lattice rule seems to behave differently than the Sobol sequence. If we look at this Sobol sequence, from our result, we would predict that the convergence rate will be close to 1.5. So in dimension 2, we would have the discontinuities dominating the convergence rate. But in the case of lattice rule, it seems that the convergence rate is dominated by this m instead of instead of the discontinuity. And then when we increase the dimension to 3, then the convergence for the lattice seems like the convergence rate of the Sobol sequence, but the dimension is off by 1. So we expect the convergence rate to be minus 1 minus 1 over 3, but here we are seeing that minus 1 minus 1 over 2. And same thing happens for the 5 dimensions. And when I'm increasing m to 0.2, all of these convergences are dominated by the m. And in the third example, I'm going to show the type of axis parallel discontinuity, that this omega is given by the minimum of this TJs, j from 1 to s, and that these TJs are larger or equal than 1/2. In these plots, we do not see the effect of the discontinuity especially for the Sobol sequence, when I'm increasing the dimension from 2 to 5, we are always observing the convergence rate that is closer to minus 1.6, which is the effect of this M. And for the lattice rule, when we increase the dimension, we see this non-asymptotic effect. And in the last example, I plotted the case for the partially axis parallel discontinuity. That the first two dimensions, we have the minimum of T1 and T2 that is larger or equal than 1/2. And for the rest of the dimensions, I have this hypersphere type of discontinuity. And for all these, okay, so for I'm plotting the dimension 4, 5, and 7, which is just 2 plus the case for the previous examples. So for all of these cases, we are not seeing the effect of this axis parallel discontinuity. The convergence rate would be it's similar to the example 2, as if we only have this hypersphere type of discontinuity. So it's time to conclude that this is a comparative study of lattice rule and Sobol sequence. We discover the relation between this variance convergence rate and the boundary growth condition. For the Sobol sequence, the effect is superposition of these two types of singularities, the boundary unboundedness and the interior discontinuity. And both sequences are insensitive to the axis parallel discontinuity. But the things that are not clear to me is that the effect of the types of different discontinuity boundary on the lattice rule is still not clear. It seems that the hyperplane type of discontinuity is more friendly to the lattice rule. Some references, and thank you for your attention.